So we're very glad to have today Sergio Gimeno Soler from Universidad de Valencia. He's doing his PhD there under the supervision of Tony Font. That is, I'm very happy to say that is with us today. So Sergio, the stage is yours.
Okay, thank you very much. First, I want to thank Professor Luis Crespino for inviting me to give this talk. Okay, if I will start. Here, I will talk about magnetized accretion disks around Kerr black holes with scalar hair. In particular, I will talk about the non-constant angular momentum disks that we computed recently in this second paper of the bibliography in collaboration with Professor Tony Font and Professors Carlos Herdeiro and Eugene Radu from University of Aveiro in Portugal. Okay, I will start by talking about magnetized thick accretion disks, but in particular about accretion disks in general, because I don't know how much you know about this. So I will start by giving a brief overview of this thing. Okay. Accretion disks appear at all scales and all kinds of objects in astrophysics, right? You can observe accretion disks in around stars, protoplanetary nebula, black holes, neutron stars, white dwarfs. So it's a very relevant kind of object. So, but we, in particular, we are interested in proving the strong gravity regime. So we are going to focus in accretion disks around black holes in particular. So around compact objects and black holes in particular are different kinds of accretion disks. And regarding their morphology, we can classify them as thin or thick disks, broadly speaking. So thin disks have this characteristic disk shape, like a DVD or something like this, and have small pressure gradients, and are present in X-ray binaries, supermassive black holes, and this kind of systems. And thick disks have kind of a donut shape, a toroidal shape. I mean, we call them disks, but they are more like tori, and have big pressure gradients, and are believed to be present in compact binary mergers. But this is kind of the classical scope of the thing, because actually recently thick disks are employed also for simulations around of disks around supermassive black holes as well, like the EHT simulations. Okay. I want to stop a bit before proceeding by talking about the stability of the disks, because this is a very important topic. Before this kind of systems are believed to be involved in several astrophysical scenarios, like the launching of GRBs, of gamma ray bursts, and the relativistic jets that we all know, these jets in the center of galaxies, of active galaxies, and also the jets in microquasars. So the presence of an instability can be a threat or a prerequisite to have a relativistic jet, for instance, like we will see in a moment. Okay. More or less, there are three relevant instabilities in the physics of accretion disks around black holes. The first one is called the runaway instability, and it's an instability that destroys the disks in a dynamical time. So the disk does not have time to serve as a progenitor, for instance, for short gamma ray bursts. But luckily, we know that non-constant angular momentum distributions quenches the appearance of this instability. Another instability is the Papaloiso-Pringle instability that implies that the matter distribution of the disk, in particular the tori, lose its axis symmetry, and it forms kind of a planet around the black hole. This is believed to be a gravitational wave radiation source if it happens. But we know that the magnetorotational instability, that is another one, quenches the appear of this Papaloiso-Pringle instability. So if we have a non-zero magnetic field, it seems that the magnetorotational instability is the one that is most important. This instability transports angular momentum through the disk and triggers the appearance of turbulence. This is necessary for jet launching. So the appearance of the magnetorotational instability is a good thing for us. So it seems, by the look of the things, that considering non-constant angular momentum distributions and magnetic fields is essential for simulations of disks around black holes. So we are now going to focus in the approach that in the formalism that we use to build disks around black holes. In particular, we will build equilibrium solutions. What does this mean? Well, so this means the following. First, we assume that the fluid does not have self-gravity. This is a good approximation if we consider that the fluid is sufficiently diluted. So the self-gravity of the disk is unimportant. And we also assume circular motion. And this is a requirement, a prerequisite to have equilibrium solutions. And we also assume a magnetized perfect fluid that has this equation of this energy momentum tensor, a purely toroidal magnetic field. This is also something we need because you can put poloidal fields in a disk, but we currently do know a way to implement a poloidal field in a consistent way. This means that the field is coupled with the fluid. We also assume ideal GRMHD. GRMHD means general relativistic magnetohydrodynamics. These are the equations, the energy momentum conservation equation, the baryon number conservation equation, and the Maxwell equations, and also that the disk, the fluid in the disk has infinite conductivity. We also need to assume a polytropic equation of state to integrate the equations, and a kind of equation of state for the magnetic field that has this aspect. Okay, next. So integrating the equation, the energy momentum conservation equation, because the other two are fulfilled identically, we arrive at this equation. The important part, the relevant part for non-constant angular momentum disks are the first two terms. In particular, the first, this W, that has this functional expression, the potential here. So to integrate this equation, we require to prescribe an angular momentum distribution, which is, in our case, this one. We prescribe an angular momentum distribution at the equatorial plane that is constant for it's constant, closer to the black hole than the innermost stable circular orbit. This this RMS means marginally stable orbit. And outside this ISCO, it's a kind of a power law, but a power law with an exponent alpha, and it's a power law in the Keplerian, in the angular momentum Keplerian sense. This means if the exponent is 1, we have Keplerian rotation. This means that every particle moves in geodesic in geodetic motion, and in geodetic motion, and the acceleration vanishes because the Keplerian angular momentum is the orbits of, correspond to the orbits of free particles. But this is in the equatorial plane. But in our approach, to compute the angular momentum that we need to compute the potential outside the equatorial plane, we use this definition. This definition allows us, this definition of the cold von Siepel cylinders is taken to be able to integrate this last term of the potential, because in general we cannot do this integral. Okay, so we will pause a bit here on accretion disks, and we'll turn to Kerr black holes with scalar hair for a bit. Okay, if you don't know, these Kerr black holes with scalar hair are a class of the called hairy black holes that are stationary and axisymmetric solutions to the Einstein-Klein-Gordon field equations. If the Klein-Gordon field is not stationary and axisymmetric, which is the key to circumvent the no-Herr theorems by Bekenstein and these people. But the energy momentum tensor that we obtain by computing, from this field, is actually stationary and axisymmetric. So our spacetime is stationary and axisymmetric, which is what we want. The line element describing the solutions, where F1, F2, and W, and F0, of course, are functions only of the radial coordinate and the polar coordinate. There is this function, and we can see if the radius of horizon vanishes, we obtain another object that is a boson star, which is very similar to this, but the key feature is that there is no horizon. So we have a star. This solution is within the framework of general relativity, is asymptotically flat and stationary and axisymmetric. So it's, very nice. Some relevant features about this solution is that the solution is invariant under a global U1 transformation of the field. This means that a conserved current and another charge, but this other charge, as the field the field decays exponentially when R goes to infinity. This charge does not possess a Gauss law, and an observer at spatial infinity does not have access to all the relevant spacetime charges. I already mentioned this. The value of the mass, the angular momentum of the black hole, and the Miller charge is not enough to determine a unique solution. So 2 additional parameters are required. This is n, the number of nodes of the solution, and m, the azimuthal harmonic index that is related to the number of nodes in the azimuthal direction. So more about these solutions, because I mean, theoretically speaking, this works, but we want to know if these solutions are astrophysically relevant, right? Because I mean, for a solution to be astrophysically relevant, it needs a mechanism of formation. So there are mechanisms of formation for this. One is that Kerr black holes in general relativity are unstable in the presence of a massive scalar field under the mechanism known as superradiance. But these numerical studies for the nonlinear saturation of this superradiant instability are very challenging due to the long time scales involved, and that is, I mean, we will require a lot of computational time. This was done not very long ago for the case of vector fields, of massive vector fields, Roca fields, because the time scale is lower by William East. But there is another mechanism to generate hairy black holes. That is the merger of bosonic stars. In particular, for the case of mergers of Broca stars, a recent work by Juan Calderón Bustillo and collaborators, they studied the merger of two Broca stars. And one of the possibilities as a result is the formation of a hairy black hole. In this case, a vector hairy black hole, but the same can happen for scalar hair. Okay, a bit more about the superradiant instability is of course the stability, but because the name superradiant instability hints to us as, I mean, what is this thing stable? So in our case, these solutions are synchronized. That means that the frequency of the field is equals to m times the angular velocity of the black hole horizon. But what happens if the hair is not exactly synchronized? So we have two options. One is if the frequency of the field is smaller, and if it's smaller, the field is superradiant unstable. So this means that the field will grow, its frequency will grow, and it will grow reducing the angular momentum of the black hole. So eventually they will synchronize. And if the frequency is greater, the hair will be in an unstable regime in which the hair will decay. The system will lose part of its hair, and it will end as well in a stable region. So there is another thing that we can think. One can think that if you increase m, the value of m, the black hole will always be in the superradiant regime, right? You start with m equals to 1, and then you are in the stable regime. But if we consider m equals to 2, then the black hole will be in the superradiant regime. If the black hole then goes to the stable regime, it will be unstable and under the M3 mode. But the time scale of the even if these kind of solutions are unstable, the time scale instability of the instability can be as great as the Hubble time. So for our astrophysical black holes, these solutions are stable. Okay. And there is one more thing. There is a region in which black holes and hairy black holes can coexist. A region in which they share the same value of the mass and the angular momentum. So in this region, hairy black holes have more entropy than their Kerr counterparts. So this means that the hairy black holes cannot decay adiabatically to Kerr black holes. So if we have hairy black holes, they will not decay into Kerr black holes under certain circumstances. So there is another thing, and that's that Kerr black holes with scalar Kerr have a maximum mass related to the value of the scalar field mass. So these values are very, very small. For stellar masses black hole, the mass parameter of the scalar field is around 10 to the minus 10 electron volts, and for black holes in the supermassive range, they are in around 10 to the minus 20 electron volts. So, I mean, we don't know if there are scalar fields with that mass, but in string theory Saxyverse, we have, I mean, theoretically speaking, we could have a sufficiently large mass range from 10 to the minus 10 to 10 to the minus 33 electron volts of particles, of a kind of a soup, right? So if this is true, Kerr black holes with scalar Kerr could be relevant at all scales. Okay, we will now move on to the results. First, the parameter space that we are considering in the study, in the case of these hairy black holes, are one solution in the region of coexistence with vacuum Kerr black holes, and the other ones do not have a Kerr counterpart. I mean, a Kerr equivalent in terms of the mass and angular momentum. This can be seen in this AH quantity that means the spin parameter computed in terms of the event horizon quantities, the mass and the angular momentum stored in the event horizon. And we can see that for the second and third cases, the values of this spin parameter are great. That is impossible for Kerr black holes. This, of course, is not a problem and not some violation of the cosmic censorship hypothesis or this, because there is an event horizon, actually. And if you compute the linear velocity of the horizon for these cases, you can see that it's actually smaller than in the first case. Even if the spin parameter of the solutions, I mean the equivalent to the spin parameter of the solutions are greater than 1. Okay. Regarding the disk, the parameter space that we computed is this. This means, I mean, these plots represent in the first line the distribution of angular momentum, and in the second one, I mean, you can more or less forget about this because it's the potential and it's not that relevant. But in the first line, you can see that we consider solutions that are more or less Keplerian. I mean, they are not that Keplerian, but I mean, we will see that what does mean. Okay, now on to this morphology. We see here, actually, in the last row of this plot, we can see what one can consider as the standard thick disk, right? These thick disks are very thick when compared to the black hole, and usually they are semi-infinite. This means that the disk is not closed. Realistic. Consider a very even they are within the framework of thick disks. They cannot be. I mean, they do not fit into what we usually know as thick disks. Okay, this is for spacetime 1. This is for spacetime 4. We observe a similar behavior. And this is for spacetime 7. And we also observe a kind of similar behavior, but of course, we can see that the aspect is a bit different between the cases, but this is related to something that we are going to see right now. We also see that the event horizon is very small in this last case, but this is related to the fact that the most of the mass and angular momentum of the system is stored in the hair. So the event horizon is very small, and this is more similar to a rotating scalar boson star that is to a Kerr black hole. So yes, perfect. When comparing the different solutions and also plotting the gravitational energy density of the solutions, we can see that for all the cases, I mean, sorry. Sorry, we can see that it appears a interesting effect, let's say, in this first row, last column, and that's the appearance of a second maximum in the energy density. This cannot happen. This cannot happen for Kerr black holes, and this is an effect that only can happen. Sorry. Sorry. Thank you. That only can happen for hairy black holes due to the presence of an extra potential well due to the scalar field. If we observe the first column and the second column, this does not happen. So this is a unique feature of this kind of solutions, right? Okay. We also noticed that we can put constraints on these models. I mean, on the acceptability of these models, if we consider a mass for the scalar field that it's appropriate for the scale of the black hole we are. A different value. I mean, we consider relationship between the value of the density of the rest mass density maximum at the center of the disk. I mean, in the location of the maximum, versus the mass ratio between the mass of the torus and the mass of the total system. If we consider a too large value of the rest mass density, we can go beyond even, I mean, even what? Sorry. Let me. We here show an horizontal line in the first row, showing showing the location of the value of 10 to the 15 grams per centimeter cube. So this is believed to be more or less the maximum that can be achieved in the center of neutron stars. So it's unrealistically high for accretion disks. And in the vertical line, we show the location where the mass, the torus, is 10% of the ADM mass. This means that beyond that value, we will have to consider self-gravity of the disk. So our approach is no longer valid. So we see that the shaded region in this first two plots is the region where our approach works. So we can have accretion disks built within our model with these values of the density and the mass ratio of the disk. In particular, in the first row, we are considering an ADM mass of 5 solar masses. This is within the range of neutron star mergers. I mean, the remnant after a binary neutron star merger or something like this. And in the second row, we are considering the mass of the black hole in the center of M87, and the value measured by the Event Horizon telescope. And in the horizontal black lines, we are showing the density range that appears in the Event Horizon telescope collaboration simulations, more or less. So in a sense, we can say that we are constraining our parameter space if we want to reproduce the values of the simulations of the EHT collaboration. This is true in a first order approximation, because the values of the maximum of the density in the case of the Event Horizon, the maximum values in the density that they report correspond to simulations. To the values that the disk has after a time evolution. So usually these values are smaller than the ones that they put in the initial state. So actually, we should consider values a bit higher, but we don't really know about this, because for this to be known, we have to perform nonlinear evolutions of these disks first. Here I show the values of the scalar field mass that are more or less what we talked about before, right? Around 10 to the minus 10 and around 10 to the minus 20 for the supermassive case. And okay, this is it. We have, these models, of course, have restrictions because the parameter space is huge. and we have restricted to a very small region of the parameter space. We have assumed a purely toroidal magnetic field, which is not realistic. Some really big magnetic fields in some cases. But we plan to do more complex studies involving. I was talking about extending this study to Kerr black holes with Kerr, self-interacting Kerr in the case of scalar and also Kerr as well, and including poloidal fields in a consistent manner, because nowadays the poloidal fields, they always put them by hand as a small perturbation. So it would be nice to have a self-consistent way to build these black holes, these accretion disks with poloidal health. And that's it.
Okay, so thank you very much. I will ask everybody to turn on their microphones for a round of applause in retribution to your nice seminar.